And then
just let me introduce Hartmut just briefly. So it's actually some of them. Anyway, Hartmut, it's a pleasure to welcome Professor Hartmut Häffner from University of Berkeley. He received his PhD in physics from the University of Mainz back in 2000. So interestingly, he spent a little bit time as a postdoctoral fellow, both in Mainz as well as in ISC Bangalore. So he spent some time here in ISC campus. And after that, he received a Fyodor Lydin Fellowship from the Humboldt Foundation, and then went to NIST as a guest researcher. Subsequently, he moved to the University of Innsbruck as a university assistant, where he held a Marie Curie Fellowship till about 2004. Subsequently, from 2004 to 2009, he worked as a senior scientist at the Institute for Quantum Optics and Quantum Information in Innsbruck. And in 2006, he won the START Award of the Austrian Ministry to build his own research group. From 2009, he has been at the University of California at Berkeley, and he's also affiliated with the Lawrence Berkeley National Laboratory. So I don't, with no further ado, I welcome Hartmut to give his talk on electrons. Thank you.
Thank you very much for the kind introduction and also the opportunity to present our work and our plans. It's a pleasure. And if you have any questions, please feel free to ask them right away. And I try to address them as good as I can. And so does this work for everybody? Can you see my screen?
Yes.
We can. Perfect.
Okay, great. Okay, good. So I will speak about our work towards the trapped electron quantum computer. And I try to, or I will motivate why I got interested in that. I think it was 2013 or so. And then we started to become serious in about 2020. And so here's the outline. I will very briefly motivate why one could be interested in quantum information processing. And then we'll come to the actual motivation of this topic. And you can basically summarize it as electrons are the better ions, at least if you want to do quantum information processing. That's the hypothesis, and we have to test it. And for this, we would like to trap electrons and in a Paul trap in vacuum. And I'm going to describe the setup, how we detect the electrons, how we characterize the ion trap, and then I will give an outlook where I'll try to address some of the questions of how such a trapped electron quantum computer could look and actually work. Okay, so just coming from the very high level, why would one want to do quantum information processing? And the claim is that quantum computers can solve certain tasks much more efficiently than classical computers. For instance, let's say you were interested in solving a Schrödinger equation for 300 interacting spins. If it's a very general Hamiltonian, you will need to solve really a Schrödinger equation without any approximations or simplifications. And then you would require more classical bits to do that than there are atoms in the universe. And that basically comes from the size of the Hilbert space, like 2 to the 300 is just a very large Hilbert space. But the field really took off when people figured out that that one can use quantum mechanics or quantum computer to factor large integers, or that you can search more efficiently in an unsorted database. Or now people are actually very much interested in quantum chemistry calculations. So if you want to build a quantum computer, if that's your premise, how would you go about this? And there are many different ways how you can do this. And I show a couple of here. You can do, for instance, nuclear magnetic resonance. You can use photons, quantum dots. The actually most prominent ones at the moment are superconducting qubits, Rydberg atoms, where you hold single atoms in optical tweezers and let them interact via the Rydberg interaction, are actually quite promising, and there's quite some revolution happening there, and trapped ions. So stepping back a little bit, if you want, not every, as you've seen, there are some technologies, but not every technology is actually lends itself to that. For instance, nuclear magnetic resonance has actually some problems with a scalable physical system size. So there are certain criteria we believe a quantum computer must fulfill so that it makes sense to actually take it serious as a quantum computing platform. And so these are the 5 criteria put forward by David DiVincenzo in about 2000. And they are kind of common sense, but it's useful if you're thinking about a quantum computing or a technology to just check your technology. Can I do these 5 things? So the first is, I want to have a scalable physical system. I want to control not only a few spins or qubits, I want to be able to control, in the end, millions. So there needs to be some sort of path forward. I need to start the computation in a well-defined state, so I need to, the ability to initialize the qubits. I need to have long coherence, meaning that the qubits don't interact too much with the environment. And I need to be able to do nearly arbitrary unitary operations. One can be a little bit more specific about it, and that's basically what's called a universal set of quantum gates. So I want to be able to perform a certain set of quantum operations, and then it's known from those I can build up arbitrary quantum algorithms. And then in the end, of course, I need to read out. So those are kind of, in some sense, very common sense, and it's important to check one's technology. Now, so I'm coming now to the motivation why one could be interested in trapped electrons. So they're using ions. Quite a number of things have been done. There are a few good things about what ions are really good at. We have really high fidelity operations, at least as compared to other technologies. So if you have 2 qubits interacting with each other, we're talking about 1 error in 1,000. Actually, the record is now 6 errors in 10,000. And for single qubit operations, we're talking about 1 error in 1,000,000. The architecture is also very modular, and that's important for scalability. So I can have little modules which are then well characterized, which then can be connected to other modules. And I will show a little bit what I mean with that. And some small modules have already been built with up to 20 ions, which work reasonably well. And then we have really long coherence time. So this all sounds good, but not everything is perfect. For instance, I show here this picture of an ion-trapped quantum computer at Innsbruck, and you see it's complicated. There's a lot of things going on. And part of it has to do with the optics. But let's first see about the physics. So we have this this vacuum chamber here. So the surrounding is very complex, but the physics is really simple. And I think that's key for actually building a quantum computer, because you want to have a simple system that you can then control and understand well. So here we have an ion trap. An ion trap, essentially you apply electric voltages to these electrodes. It's an alternating voltage at around 30 to 50 megahertz. And that creates then a confining, time average a confining potential. And then ions are trapped here in the center of this ion trap. So you can see here, for instance, an image of 3 calcium ions. So that's a real CCD image. And you can see the ions here lining up because the confinement in the transverse direction is relatively strong. And they're spaced by about 5 micrometers from each other. So you can optically resolve them. They can also poke lasers at them and can say, okay, I want to talk only to, let's say, the center ion here. Each of those ions represents then a qubit. and I can laser cool it, manipulate it, read it out, and do all sorts of things with it I need for quantum information processing. So this is all nice, but there are some problems here. And one problem is that we control the qubits optically, and that's more complicated at the moment than using, for instance, buying a radio frequency synthesizer and programming a radio frequency synthesizer. I need a laser source, then the laser, I need mirrors to align everything. I need to get the light into the fiber. I need to switch on and off the light. So it's not so easy. And you have seen much of what I showed before, this crazy stuff around has to do with that. And then it's also relatively slow, and that has to do with the mass of the ions. In order to actually mediate transfer of quantum information, I need to push on the ions, and then the other ions need to move. That's the way, I will talk later a little bit more about this mechanism. That's the way how we mediate interactions between qubits, and that takes, let's say, tens of microseconds is a good time scale there. And that has something to do with the mass. It's heavy, and therefore I need a lot of force to get them moving. So here comes now why electrons are better. And it can be, or I think, or I claim here that electrons are better. Of course, we have to prove it. But here's the motivation. And it can be summarized that electrons are simple and light. And what I mean with that is electrons are light. They're about 70,000 times lighter than the calcium ions often are used. And they are also simple. They're just a two-level system. There are only two levels. You know that pretty much any physical system is not a two-level system. If, for instance, the ions, there, yes, we isolate two levels, but there are many more levels, and that can lead to problems. So it's a spin 1/2 system, and that allows for very high fidelity operation because there are only two levels. I cannot end up in a third level because the third level doesn't exist. The spin in a magnetic field has also reasonable radio frequency transition, so I have all electronic control. And it's the lightest charged particle, and that basically has a small mass, and that speeds up the operations. And one could say it's the lightest. Well, we have also neutrinos, but I don't want to do quantum computation with neutrinos. And photons don't have a mass, so I have a hard time trapping them and holding on to them. So that's the motivation to actually use electrons. So here's now the idea of the next 30 minutes or so. We want to replace the ions in an ion-trapped quantum computer with electrons, and then do everything like we want to do it with trapped ions. So that's kind of the idea. We want to retain most of the good features we have of the trapped ion approach, and addressing the challenge, for instance, we have with optics and speed. So here is now the kind of idea how one can hope to scale trapped ions to larger numbers. So you can see here these individual modules where various number of electrons or ions can be trapped. And so this is for the trapped ion proposal originally. And then you can shuttle the qubits and can say, okay, now I want to have qubit 955 interact with qubit 5672. You bring them the same trap zone, and then you let them interact, and then you move them around. And this allows you to flexibly interconnect them while having actually modules available. And I think that's a very clever idea, and I think this is what we should be really striving for. And yeah, the idea is to replace the ions with the electrons. And so this is what I want to talk about now. What we hope to get then is actually all electronic operation. It's just switching voltages and radio frequency. Relatively large clock speeds on the order of like 1 gate per microsecond. Long coherence times. Temperature, we are talking about 100 millikelvin to 4 Kelvin. That's what we need, I think. There's no lasers involved. Very little optics, I should say. Easy to interface with circuit-based quantum information processing. That's for the specialists, maybe interesting. And it's about 100 times faster than the trapped ion approaches using a similar ideas, what I'm talking about here. In terms of comparison to superconducting qubits, you can say that there are less stringent cooling requirements. We think we need to go only to maybe we can get away with 4 Kelvin. Maybe we have to go to 100 millikelvin. The coherence times are vastly improved, or we expect them to be vastly improved. And maybe most importantly, there's a higher connectivity. With superconducting qubits, at the moment, we mostly have next neighbor coupling or fixed couplings. But here we can transport the electrons around, so we can then hope to have arbitrary coupling. So, of course, there's a catch. Nobody has tried trapping electrons yet. We don't know what the difficulties are. And so this is what this talk is about, trapping electrons and getting started and figuring out where the problems are and see whether we can address them. So we want to go from ion qubits, where we're using optical frequencies, lasers, radio frequency to trap them, let's say 20 to 40 megahertz at room temperature, to electron qubits, where we have microwaves to control them. That's easy. But we need to drive the trap at about 10 gigahertz because they are so light, and it needs to be cryogenic. So how to get from ion qubits to electron qubits? And the first step is to trap. In order to trap electrons, we estimate that one would need a few years and about $1 million. Or we go a little bit a detour and not go directly cryogenic and trap at lower trap frequencies and bigger traps, and then we can get away with actually substantially less hardware. I should say that the experiments I show, we invested about $4,000 in the whole experimental infrastructure. The rest was coming from scrap and old experiments, so really very low key. So that was a lot of fun to build it up like this. But it's going to be room temperature, and then we have the demonstration now, and then we can get a little bit more serious and go cryogenic. So what do we need in order to go after this? We need an electron trap. We need an electron source, and we need an electron detector, and this is what I'm going to talk about. The electron trap, this is the idea. So we have 2 AC electrodes where we apply the oscillating electric fields, and this is ground. And this then leads to quadrupole field where the electrons would be then hopefully trapped in the center. What we do is that we use a PCB board, cheap to manufacture, and we have then 3 layers. 2 are ground, the bottom and the top, and the AC or the microwaves are in the center. And then hopefully the electrons will be trapped, and this is kind of a more concrete layout to give you some ideas. So we use some Rogers material. The dimensions are order of millimeters, and the smallest feature size is 150 microns. So it's not crazy, and it's a kind of a standard fab process. So you can order it for, I don't know, $100 or so, such a trap. And we simulate the trapping potential, 90 volts, we assume at 1.6 gigahertz, and then we calculate what we call a pseudo potential, the effective potential. So you can see this here, and you can see here the effective potential. So here's the bottom, that's where the electrons would be trapped in the X direction, and the Y direction is the horizontal direction. Yeah, the potential looks a little bit different. So we have slightly different trap frequencies, but in the 2 directions, but it's not so bad. In the in and out of the plane, we apply DC voltages. Let's say if you make one end negative and the other end also negative, the electrons would like to stay in the center. So that's fairly straightforward. Trap depth order 1 eV. So here's what the board looks like. So we have, this will be the trap here, and that is a microwave resonator. It has a certain length so that we get a quarter wave. And then the RF is coupled, or the microwaves are coupled in here. It couples over, and then it resonates in here, and you get a voltage maximum here and a voltage minimum over there. This is Yeah.
Hartmut, there is a question from
Yep.
Kaushik Majumdar. Yeah. Kaushik, go ahead.
Yeah, sorry. I had a question a couple of slides back, actually. So what's your plan for the coherence time of 1 second for the electrons? Are you going to cover that later? Then we can skip.
Oh, yeah. So I'm not really saying more about it, other than that this has been achieved with an ion where the electron was had the same the electron in that ion has the same magnetic moment. So we know that the magnetic field can be made sufficiently quiet that you reach roughly a second coherence time. So this electron is trapped in vacuum, and the only meaningful shift on the qubit levels is actually magnetic field noise. There's no real spontaneous emission happening at, let's say, 100 megahertz, and it's all the magnetic field strength which matters. And so this is where this 1 second is coming from. Does that answer your question?
Yeah. Okay. Yeah, but it's still trapped in a solid state, right? So
no, it's in vacuum.
It's in a vacuum. I see. Okay.
Yeah. That's the difference. Yeah. It sits in vacuum, and the nearest surface is 30 micron away. Yeah, that's important. Of course.
Got it. Yeah. Thanks.
Yeah. And then it's limited really by magnetic field noise. We know that pretty well. So yeah, this is basically the trap here, and you see here that basically the electrons will be trapped, basically essentially here. So this is the AC electrode, and I showed the cross section, and then on the top and the bottom we have these 10 DC electrodes, so in total 20 electrodes, and we can apply the right potentials to actually prevent the electrons from escaping along this horizontal direction here. And yeah, then there's the board here on top and the board at the bottom, and then we screw it together, and that basically gives then the electron trap, I should say. So we take a vacuum chamber, which we had lying around, and then basically we mount the ion trap in here. So you can see now this 3-layer board. The center is the radio frequency, and then the DCs are on the outside. And so that forms the ion trap, and the actual ion trap sits here. I don't know whether you can see this here. That's where the electrons are then trapped. We put that in UHV. We apply about 5 watts and then get about 100 volt AC, which then leads hopefully to trapping. So that's basically the bare bones of the experiment, but now we need a little bit more infrastructure. So one thing which we need to do, yeah?
Hartmut, I have a question. So in this, how do you have a control over the number of electrons in that trap, or are they limited by the Coulomb interaction?
Yeah. We do not have control over the number of electrons in the sense. So, okay, what we do is we empty the trap and then we load for a certain amount of time. And then we can control the average number of the electrons this way.
Okay.
And so this basically comes back to when I want to build a quantum computer, I need to control the number of qubits, of course. And then I need to detect them in a non-destructive way. You will see that later we detect them destructively, so we can tell after the fact maybe how many electrons there were. But that's, of course, not good enough for a quantum computer. So we need to come up with a different detection scheme, and I mention that later. And then if you can detect the number of electrons, then you have means to control them. So basically you would load until you have a single electron, then you stuff it away in somewhere else, then you load the next electron. This way you then know exactly how many electrons you have, where they are. And at cryogenic temperatures, we expect the lifetime of those electrons to last until the next time there is a blackout and the power in the lab goes away. So there's really not a loss mechanism at 4 Kelvin for the electrons. Does that answer your question?
Yeah, absolutely. Go ahead.
Good. So before we detect them, we need to create them. And it turns out that the electrons need to have relatively low kinetic energy and enter our trap. Our trap is an EV deep, but still, I mean, yeah, if you're coming in with more than an EV into a conservative potential, it will just roll out at the other side of the trap. And yeah, they need to be inserted into the trap. And yeah, so what we came up with is actually photoionization. And the way this actually works, oops, oh, what happened here? Okay, then I need to explain it. So the way this works is that we heat calcium, and then we send a beam of calcium through the trap. And this is neutral calcium, so it just flies with its thermal velocity, with its thermal energy through the center of the trap. And that's, let's say, about 50 millielectron volt. And then we come in with laser light and photoionize it, meaning we detach a photon just above the threshold. So we give the electron just enough energy to escape that atom. And then we have an ion continuing to fly on. And because it's heavy, the ion, it carries most of the energy with it. And the electron has only very little energy, very little kinetic energy. You imagine that electron moves only with 600 meters per second, but it has really tiny mass. And that's why this electron has then, if we do tune everything right, only like a couple of millikelvin of energy. So it's really cold. And that is then created, born in the bottom of the trap, and that's where it should be trapped. So that's the idea. So, and what you can see here, this is a little tube. That's where calcium is in there. We heat that, and that calcium comes out, flies through the trap. And then we have a bunch of lasers here. It's actually 2 lasers in the blue at 400 nanometers about, which photoionize the calcium and create those electrons. So that's all the optics we need. And here you can see an image of the trap. So you can see the DC electrodes sort of. This here is actually, now I need to think, this is probably the atomic beam, and the laser beam comes here from this side, I would imagine. Anyway, so this here is fluorescence from atoms, and that's part of the process in order to generate the electrons. So, yeah.
So how do you make sure there is only one calcium ion that has come?
We do not measure that. We do not control that. So we send many calcium atoms through and try to generate electrons for a certain amount of time. And we adjust that time so that we get, on average, let's say 0.1 or 1 electron, or maybe 10 electrons, depending on what we want to do. And we control this by how hot the oven is, and also for how long we load. And again, in the end, the number of electrons is controlled then only after the fact when we measure it. And so what we need is this non-destructive detection, and then we can control really the number of electrons. This is how we do it with the ions also. The process itself is statistical, but we sit then there and count, okay, now we have 1, 2, 3, okay, I want 5 ions. When I have 5 ions, then I stop loading and I'm happy and I continue with my business. If I loaded 6 ions and wanted 5, well, then bad luck. I need to start all over again and dump all ions. So that's what we do at the moment with the ions also.
Okay, yeah, thanks. And what happens to the ion? It does not, disturb the electrons because that's still staying there.
Oh,
right?
yeah, that continues to fly off. Yeah, and the trap is actually repulsive for those. So turns out that yeah, they are not trapped effectively.
Yeah,
ion.
makes sense. Yeah, of course. Yeah.
Yeah, and it's not, of course, because it's an AC field, so it actually works for both charge states. But then we have also this additional DC field, and that's really repulsive.
Yeah, you should be having a biased DC. Yeah, that's right.
Yeah, exactly.
Yeah.
But we could arrange the trap in a way that it wouldn't, but then it turns out that the trap parameters are just not very stable. So you would have a very shallow trap for the ions, and I would bet my life that you would lose them still.
Sure. Yeah.
Okay. One question from Arindam. One more question, Hartmut, from Arindam.
Yeah. So you said that you don't really control the number of electrons. It's more statistical, right? I mean, you said that it could be more than one. It could be an average number of electrons that's left.
Yeah.
But then my question is that then how do you determine the number of states there? I mean, if you have, per electron is just 2 states. But if you've got multiple electrons, then how do you determine the number of states in the trap?
For quantum computing, we need to really know the number of electrons. So for quantum computing, the idea is to trap them one by one. So to have multiple trapping zones, let me see whether I have, So the idea is, for instance, I try trapping an electron here. I try until I have trapped exactly 1 electron. And I can do that if I can detect the number of electrons. So let's suppose I have now 1 electron here and no electrons anywhere else. Then I can move this electron over here. Now I know I have 1 electron here, and then I go here back and try to trap a single electron until I'm happy. If I have 1 here, I move it over here. And this is how I can continue basically filling up the quantum register.
Okay.
That's the idea. And we do that with the ions. We effectively do that exactly this way. Not quite exactly this way. We can, right? I showed in the beginning that we have this time. So in the beginning, I showed this image here, right? And yeah, you load ions, and we set the loading rate in practice so that every 10 seconds we load another ion, right? You look at it, the screen, and you say 1, 2, 3, 4, or so, and then, now I have the right number of ions, and then I stop loading. I switch off the lasers, and that's it. Okay, so where were we? Somewhere here. Okay. Good. Then the next things we need to detect the electrons, and I will talk later about how we actually want to do the non-destructive detection. But at the moment, we just apply a voltage pulse to the trap. We eject the electrons, for instance, through the top, through that slit, and that goes then on a microchannel plate, where we get with a high probability counts or an electrical signal if there was an electron in the trap. So that's our trapping scheme at the moment. In case you're interested how a microchannel plate works, but maybe you guys know that already, or know that you have an electron, it hits basically one side of an electrode, and I have a large voltage gradient, and I accelerate them down, and I get an electron avalanche, and then I get a measurable signal in the end out of it. So this is the vacuum chamber as we have it now, and basically the microchannel plate sits over here on one side, and this is where we then detect them, the electrons. So this is how it looks in real life. So what I just said, so you can see here the board, there are the connections, the electrical connections, quite a number of them. Here's the microchannel plate, here's the mesh. And here you can see the oven actually here. Okay, we put everything together, and then we start trapping electrons. What's cool from an ion trap perspective is this. This is the apparatus. Actually, we didn't have a lot of space, so we put it underneath the desk. So this is where the experiment was located. And you can see it's essentially the vacuum chamber, some pumps, and then that's the optics we need to actually photoionize the electrons or the ions. And this is our electronics, and this is basically what we mostly got from trash. Old synthesizers nobody wants to use any longer, power supplies, and so forth. The monitor is actually not used for it. And this is to compare to roughly this, right? So here's
sorry, one more question here. So your the detection is still a destructive one then, right?
Yes. Yeah. I will talk later about how we want to do non-destructive detection. Yes. So here's the signal. kind of the measurement cycle. We leave one stage for the photoionization on all the time. And then we pulse this 390, which does the second stage, into the continuum, and that actually creates the electrons. So the trap is on all the time, and then we load for a given amount of time, order of a few microseconds or so. We load electrons, then we wait for some time, where we can do various things. I will explain it. And then after a certain amount of time, we give it a voltage kick, the trap, to eject the electrons towards the microchannel plate. And so this is actually here an experimental cycle, lasts about 20 microseconds or so. So this here is the loading rate, the loading time. So you can see actually electrons arriving with a certain probability, 10 to the minus 3 per 1 nanosecond bin at the MCP. Actually, you have to divide that by 200 because this signal is blown up by 200 so that you can see it. And then when we actually eject the electrons, you can see many more, like 3 orders of magnitude more electrons arriving at a very narrow window. And these are actually the trapped electrons. So that basically is the idea. And of course, when you create lots of electrons, of course, some electrons will also hit your detector. So, and then you can basically look how many electrons did we trap as a function of loading time. And here you can see now, this is of course the average number. And you can see now that if I want to load on average 1 electron, I need to load for about 30 microseconds or so. So that's kind of the way how we can, all the control we have over electrons. And you can see that we get up maybe to 6 electrons, maybe 10. We did not really push for how many electrons we can detect there. And at some point it gets also very tricky from the microchannel plate to figure out how many electrons did you actually have the microchannel plate on the microchannel plate. For an ion trap, a more interesting. Yeah.
One quick question. So we use, in your system, are the electrons not really interacting with each other? Because the time between 2 and 1 electron should be different, right? Depending on.
Yes. So there is a Coulomb interaction. So they repel each other. And if the trap is too full, you cannot add more electrons. So that's one thing. Yeah, that's the main thing, I should say.
Okay.
There's not, but the trap is relatively large. To give you an idea, electrons in this trap probably would be separated by order of 10 micrometers. So you can, if you have a trapping volume, let's say of 100 by 100 by 100 micrometers, you can trap order of, let's say, 1,000 electrons in this trap.
Okay.
And then you get space charge limited. Yeah.
Okay.
It's not quite as
simple. Would that limit?
Yeah.
I'm sorry. I just wanted to add the question that whether that would add to the scalability of such a protocol of.
Yeah. Yeah. So basically for scalability, we're really talking about this many different trapping zone architecture. So, and that's where the scalability then comes in. And so you would, for scalability, so for quantum computing, you would not want to have more than 2 electrons per trap. And this has something to do with that it gets very difficult to control their quantum state if you have more. Let's say if you put 1,000 electrons in your trap, how do you talk to this specific electron which sits at that location? It's nearly impossible.
Right.
So, but if you have them in different traps, then it's a different thing. So that's essentially that's where it comes to scaling, right? So there's this argument has been made by solid state people. Oh yeah, we have lithography. We can produce an arbitrary number of qubits. Well, using electrons as qubits is as easy as that. I take this pair of scissors and I have 10 to the 23 electrons in there, but it's not a quantum computer. And it's not about making the qubits. It's about controlling them. So yeah.
Yeah. So one question related to what Arindam asked. So in solid state, for example, we do Coulomb blockades, right? So where you can actually, confine, maybe one electron if you want.
Yeah.
But so what's the challenge here really? Because you cannot do lithography here. So is it coming because of the fabrication? I mean, what stops you from making a very, very tiny volume of trap?
Okay, so I think there's a lot of questions here. So what makes us from making a tiny, we can make a very shallow trap which could hold only one electron. I think that could be done. But that's not really the problem. I mean, we would like to have deep traps so that we can hold on well to them. We can get exactly one electron into the trap. I think there's no problem. We need anyways a detection mechanism. So there's no way that we can avoid that. We need some detection mechanism. And once we have that, then we can control the number of electrons. What of course would be nice to make these traps as small as we can. But what's happening then is that the electrons will be close to the surface of the solid state, and there's noise coming from solids. And especially what we worry a lot about, because electrons are charged, is electric field noise. And it turns out that this is actually going then to let the electrons move in a random way, and that will be then hard to actually do quantum operations on the electrons. The way we're setting it up is we would like to have the electrons as cold as the environment, so that wouldn't really heat the electrons out of the trap, but it leads, you can view it as random kicks to the electron motion, but we want to use the electron motion to mediate the quantum information, and that's basically where then the problem is, making the traps too small. So basically, it's all about, in the end, electromagnetic hygiene. Is the environment low noise enough for what you want to do? Now, the good thing about using the spin is that the quantum information is relatively safe, or it is safe from electric field noise, I would say, and magnetic field noise tends not to be such a big issue as electric field noise. But then in order to mediate the gate, so this is for all qubits, it's the same, it's a very similar thing. And actually John Martinis calls it neutrino. So basically he says to make the qubit like a neutrino. And so the best qubit is a qubit which doesn't interact with anything, because then it has a very long coherence time. But that's not a good qubit, because if I have such a qubit, it will not interact with other qubits either. So I have then two qubits, they are immune against external perturbance. And so you think, oh yeah, great. But no, I cannot have them interact. So I need a qubit which is not sensitive to the environment, but is sensitive to the state of other qubits. So that's a little bit the challenge here. And so in the end, you need a mechanism how to let the qubits talk to each other, but avoid that the environment talks to the qubit. And the way we do this with trapped ions and want to do this with trapped electrons is actually use the motion of the electrons. And that basically means that we would couple the spin to the motion. But now you can imagine, if you do that, then if the motion gets disturbed, also the spin gets disturbed. So in that during the quantum gate, we are prone to this kind of decoherence. And that's kind of the thing why we would like to keep the surfaces as far away as reasonable. Does that kind of address your...
Yep, thank you.
Okay, coming back to actually, yeah, so here we trap on average, I guess, a certain number of electrons. Let's say a little bit more than 10%. And then after we have trapped, after we've loaded them, we wait for a time which is here on the x-axis, and then we record how many electrons do we detect then. And you can see something here that most of the electrons, let's say 10% of those which we trapped, leave during the first 100 milliseconds, but then there's a fraction of electrons which is stored much longer. And I could now go into the detail. This has something to do with how a Paul trap works. A Paul trap has, or very likely, we would like to learn to really confirm this, but it's from this numerical simulation. It's looked like the Paul trap has regions where the motion is chaotic and where the potential is really conservative. And we believe that those electrons which survive for a long time are the ones which have been trapped where the motion is non-chaotic, and those are the ones where there's chaotic motion, so you don't lose them immediately, but small perturbances will then lead to the electrons actually falling out of the trap. And this is also expected if you have multiple electrons in there. That's another mechanism how you get nonlinearities, and then if you're in a chaotic regime, you will actually gain energy and the electrons will leave the trap. So that was a little bit surprising, but I think we have now the numerical simulations. From numerical simulations, we have understood it, I believe. And then another thing we are interested in is measuring the secular frequency. So these electrons are trapped. What is their resonant frequency? And what we do there is during this wait time, we shine in microwaves at a particular frequency and then see when do we get actually loss of electrons. And you can see here at relatively low power, you can see here at 30 megahertz and at 300 megahertz we lose them, and that corresponds to motion of the electrons along. And also the simulation confirmed that along the axis of the trap versus perpendicular. And then if you blast in a little bit more power, we see higher harmonics of this 30 megahertz resonance. So that's basically what we do there to characterize the trap. And it turns out that our simulations and these measurements agree within 5% or so. So it's a pretty good agreement, I would say. So that's all I want to say to the actual experiment. And how are we doing on time? Maybe is there still 10 minutes or so?
You can take longer, Hartmut, as you wish. I think there will be a lot of interest in the detection aspect.
Okay. Yeah, you interrupt me. I have time. No other meetings tonight. Okay, so now I want to turn more towards the future, what we really want. So, and here I come back basically to the DiVincenzo criteria. And we want to have a scalable system. And for this is why I focus here on what we call the quantum CCD architecture, where basically quantum charged coupled device. So this is the idea, where we have these individual charges moving in this array of traps. We need to initialize the qubits. And here is the idea, right? So we need to have the electron in a particular well-defined state. And the idea is if we can measure the spin direction, then we can do the following. We measure the spin if it's in the spin we want to. Let's say we want to initialize it in spin down. If we measure it in spin down, then we say, okay, we are happy. That's what we want. If we measure it in spin up, then, oh, that's not what we wanted. Let us flip the spin by a pi pulse, and then it's going to be spin down. Right? So that's the idea to initialize the qubits. So whenever you have a measurement, you have already solved the initialization problem. Yeah, then we need long relevant coherence times. I think it's a single particle in vacuum, so we have pretty good control, or we know what to expect. And so I have very little doubts that there will be a problem. The difficulties of what we want to do basically are back here with creating a universal set of quantum gates and the qubit-specific measurement capability. This is where the tricky bits are, in my opinion, and I will talk about this now. So to set the stage, we wrote and published recently a paper which discusses basically the technicalities. And this is from this paper, how we envision the geometry to look like. So the trap is a little bit different. We will see whether we go with this trap. We assume that we have 20 volts on our AC electrodes at 15 gigahertz and trap then electrons here above the surface, about 30 micron away from the surface. These DC these electrodes are then, let's say, in a 4 to 8 Kelvin environment. And then most notably, and this is for detection, we have a tank circuit on LC resonator between two electrodes. Let's call this the pickup electrode at the top, and at the bottom AC coupled, for instance, these electrodes here. And what then happens, you can imagine if an electron oscillates up and down, it's going to induce an image charge. When it's up, the electrons have to go actually through the bottom. Electrons are repelled from the pickup electrode. If the electron oscillates down, it's vice versa. So there will be an image current which flows then over this electrical circuit. And you use an LC resonator to create a high resistance at high frequency. At exactly what you're aiming for is to have that LC resonator resonant with the motion of the electrons, let's say 1 gigahertz. So you would take a 1 gigahertz resonator and you measure the voltage across the inductor or the parallel LC circuit, and then you amplify it. And if you do so, you actually measure the current of the electrons. And it turns out when you analyze this, that with a amplifier which is limited at Johnson noise, let's say 4 Kelvin, you should be able to detect the presence of electrons in less than 10 microseconds. So which is pretty good. And so you basically would see an oscillating current, and in 10 microseconds you could tell, is there an electron, is there no electron, or actually how many electrons there are. So that's basically the basic mechanism how we would want to detect the presence of electrons. And this scheme, I should really include data here, has been done, or like, some graphs, has been used for the famous high precision measurements of the G factor of the electron in penning traps. So this is not dream work. This is actually used by Hans Dehmelt and Jerry Gabriels on a regular manner to actually detect and cool their electrons.
Can I ask a question, Hartmut?
Yeah.
Sorry, I didn't understand the direction of the. So this is like depending on the spin, the electrons get deflected in different directions.
That comes later. Yeah, that comes later.
Okay.
This is just the motion of the electron inside the trap. So it's the electron is trapped. It's at a finite temperature and oscillates back and forth. That's all there is right now. What you are referring to comes now next. Yeah.
Okay, you mentioned a magnetic gradient. That's the part that I was curious about.
Yes, that's what's
okay.
coming.
Okay.
Yeah,
okay.
Exactly. So now, in the end, we want to detect the spin direction. We not only are satisfied with detecting whether there's an electron or not, we want to know which state it is in. And now for this, this is where I think the biggest challenge is, we need a magnetic field gradient, or we want to use a magnetic field gradient. And in the magnetic field gradient, spin up will be pushed in a different direction than spin down. So because the potential is just the magnetic moment times the magnetic field, and if the magnetic moment is the opposite, then the potential will be in the opposite direction. So now how do you use this? So in this scheme here, I can measure when I take the signal and I look at an oscilloscope or a spectrum analyzer, I can see a peak, or actually it turns out it's a dip, of the electron motion. So at the motion of the electrons, I see a signal in my spectrum. Now, what I can do is I can now drive this motion on purpose with this electric field gradient. So I have this, not the electric field, the magnetic field gradient. So it oscillates back and forth and pushes the electron back and forth. And now you can see, I don't know whether you can see the video at the same time, but you can now imagine if you do that, that depending on which spin state is, the phase of that oscillation is different. Let's say you start with an electron very cold in the center of the trap, and then I switch on this magnetic field gradient, which oscillates with the trap frequency. I create a coherent state whose phase will depend on the direction of the spin. And you can measure that phase simply by looking at the electronic signal, the induced current. And yeah, depending on the phase of that oscillation with respect to your drive, you know then basically which state the electron is, whether it's spin up or spin down. So that's the idea of the measurement. Is that reasonably clear?
Yes. What are the typical distances the electrons are moving here? Because, you know, for this gradient.
Yeah. So the important numbers here, if I recall correctly, is that the extent of the ground state wave function is about 100 nanometers. And we need to overcome the Johnson noise. And there the extent of the motion is order, let's say, 1 to 2 micrometers. So that's basically what we talk about, motion amplitude of a 1 to 2 micrometers. Okay. Yeah, here you can then see, basically you get the spin emission force, then you get this electronic detection, you induce an image current, and you measure the phase of that image current. So that's the idea.
Vibhor have a question. Vibhor, do you have a question?
Yeah, thanks, Amrish. So just want to get clarity on the readout part. So as I understand, the spin is coupling to the motion in the trapping potential. And the coupling here, is it changing the frequency? Like it's like a sigma Z type of a coupling or sigma X type of a coupling?
Yeah.
Just to understand, you know, what's going to be a Q and Q.
It's okay. Let me think that I get this right. It's a sigma Z times X coupling, where X is the X operator, the position operator A plus A dagger. Or maybe it's actually the momentum operator. Yeah, it's a force. Yeah. So, but the trap frequency is not changed. So this is different from the Demet experiments, where they use a static magnetic field gradient to actually distinguish the spin directions.
I see.
So, so it is really like, it's spin dependent. That's the sigma Z operator on the spin. So which direction the spin points. But then it is really leads to a different amplitude on the different phase of the amplitude. But there's really like, the particle gains energy during this process. If you would continue with this magnetic field gradient oscillation, basically the amplitude starts growing and growing.
Right. Yeah. Okay, thanks.
So does it have to be a multiple of the frequency? Are you trying some form of a parametric amplification?
Yeah.
Or,
Now we're getting into the weeds, right? So to overcome the initial Johnson noise, or the initial temperature, we cannot use a parametric resonance. Once we have overcome the Johnson, the noise, we can amplify this with a parametric resonance further. And this is the idea, and that can be done electrically, because then we don't need to be state dependent any longer. And this has been described in one of our papers, I think from 2016. The first author is Peng. And there we use basically a two-stage scheme, because this magnetic field gradient is a relatively weak force. So you can create some amplitude And once you're above the background thermal noise, then you can amplify further so that you have an easier time measuring it. So that's the idea there. And for this, the second stage would be a parametric amplification indeed.
So what will happen if you directly drive it at the frequency? I mean, the parametric resonance, if in the presence of high noise, does that, what will happen to the electron?
Yeah, so if you do that electrically, so the problem is if I want to use a parametric drive, I need more force to get something done because it's a higher order process. And electrically, we have enough force. And you could drive it parametrically, electrically, but then you're just going to amplify or squeeze the noise, I should say. But you don't get any state-dependent evolution of the motion. You just get excitation and the spin is not involved. So the important thing is to involve the spin. And this is why we use the magnetic field gradient. But that force is relatively weak. And I fear if you would do that parametrically, you would just not get anywhere. That it would be very hard to get the motion of the electron to change.
Yeah, I'm sure the details are in the paper. Please go ahead.
Yeah. And if you have questions there, feel free to reach out to one of us. Okay, so this is about the detection, but you can use the same trick to run a quantum gate. And so I added this slide here. So it's again the same idea. I have a magnetic field gradient and it pushes the ions in different directions. And you can now think of, let's say, a quantum gate like this. So let's suppose I have 2 electrons in my trap. So I have trapped 2 individual electrons. I merge the potential and the 2 electrons come together and they're in the same trap now. And now I do the following. I apply this magnetic field gradient. It oscillates back and forth. And now you can imagine, let's say both spins point in the same direction. There will be a force, and that force will be in the same direction. What that means is I can excite the center of mass mode of that electron crystal. But if the electrons are in opposite spin direction, the force opposes each other, and I cannot excite the center of mass mode. And what I do now is I use that magnetic field gradient and I tune it close to the center of mass mode frequency. That means I cannot excite the stretch mode because I'm off resonant, far off resonant, but I can excite the center of mass mode if the 2 electrons are in the same state. Now I have that drive closely resonant, not quite resonant, but slightly detuned, let's say about a megahertz detuned. What now happens is that this external drive is initially resonant, but then because the motional frequency and the drive don't match, I get a phase shift. And at some point I have the opposite phase shift and I start de-exciting the electron. And I know when that happens at 1/1 megahertz, at that time, the electron motion is again in its original state, is as I had nothing done on the motion. But here's the crucial part. During that time, in 2 of the cases, the electron was excited, or the electrons were excited. In the other 2, they were not. So they had more energy during that time, and that leads to phase evolution. So and that basically realizes a phase gate where I acquire a phase if they're in the same state, and I require no phase if they are in opposite states. And that basically is this conditional phase shift, what is required for a phase gate, and that turns out is a universal quantum gate. So that's the idea, to actually have the electrons interact with each other and create a, that universal set of gates. And this is, maybe I should say, this is probably a lot to unpack for you guys right now, but if you're interested, this is how pretty much, in essence, all ion trap gates work in a very similar way. You can understand them in a rotated basis typically, but you can understand them this way. And so people, the geometric phase gate is a direct cousin of this gate here. Yeah, so Of course, there are many experimental imperfections one has to worry about, and we basically did some extensive simulations where we looked at 6 different things which can go wrong, and we tried to estimate the impact. And basically what you should take away maybe from this slide is that we looked at motional heating, electric field noise, where the motion gets disrupted. We looked at that the trap frequency might not be constant. We looked at that the trap frequency varies very quickly. We looked at, oh, the magnetic field gradient is not homogeneous. We looked at the that the trap potential is anharmonic, and we looked at qubit coherence. And what you can see here in these black bars is our estimate for the size of these noise sources. And then you can look where it intersects. And it's maybe noticeable that we can do some dynamical decoupling. So we should rather focus on this orange. And this is the naive way. And on the y-axis, we have the error rate. So what you can see for all of these noise sources, we are talking about expected error 1 in 10,000. So that's basically what we hope, or what we are pretty sure we can achieve, if we didn't miss anything, right? So that's basically for us the green light to go ahead, because if we could not get smaller error rates, then let's say fundamentally, then 1 error in 100, this would be a no-no, and there would be no point in really pursuing that architecture. But of course, right, we have to demonstrate that we really can get there, but at least there's fundamentally, we don't see any problems here. So that brings me kind of to the end. So I talked about how the system is scalable on the very high level. There's a lot to understand, of course. If you really want to scale, you worry about power dissipation, you worry about crosstalk and all sorts of things. But I think the QCCD architecture is a very powerful idea here. I mentioned quickly how we can initialize the state of the qubits if we measure them. I said that we have long relevant coherence times. The electron has a G factor of 2, the same G factor a calcium ion has in the S state, and for an S state in calcium, 1 second coherence time has been achieved. That was at room temperature. At cryogenic temperature, it will be easier to get longer coherence time. And yeah, and then I spent some time discussing how to actually do a geometric phase gate and how to read out the qubits. So, and I believe if we manage this last point here, then we are on a good way and have a good chance of making this actually working. So yeah, I want to thank you for your attention, and especially also the team, especially Can and Izzy and Neha and Alberto are postdocs on the project. So Neha is actually from Bangalore, so you might know her. I should also mention that we have very good collaboration with UC Riverside, Lawrence Livermore National Lab, also Robert Tyler Sutherland, who's now at University of Texas, and NIST are interested in what we are doing. And I also want to mention our past members, Pai Peng and Clemens. We actually came up with the readout scheme, and Nikos actually studied first how to use trapped electrons for quantum computing, and Tim was actually a fantastic undergraduate student who's now at Michel Lukin's group. And then, yeah, this was actually fun. I mean, Keysight really made this happen. David Root came to me, hey, can I give you some money and you do a cool project? And this is what we came up with. And now the Air Force. So, and that was then brought this to the electron trapping, and that was then enough to convince some more traditional funding agencies that this is a good idea and to pursue. So summary, so that maybe we can have some follow-up discussion. We trapped electrons in a Paul trap for the first time. We don't see really loss of the long-lived electrons. We have about 300 megahertz trap frequency at the moment. We really would like to have a gigahertz so that we get lower in excitation harmonic oscillator. And I believe this is the first, probably not the most important. I think I should not say this here, but it's a first step towards a quantum computer using trapped electrons. Yeah, so the goal is really to put trapped electrons on that map here of technologies with which we can do quantum information processing. So that's all I have tonight, or this morning.
Fantastic, fantastic. Thank you. Thank you so much, Hartmut. I think we already asked you many questions during the talk, but still maybe we can take a couple of questions more if the audience has any. One question I had for you was the importance of being at around 1 Kelvin in this experiment. Mm-hmm. Where all does this affect experimentally?
Oh yeah, yeah. So actually, here's the let me go jump directly there. I should have really have a few more slides about electronic detection because I did my PhD in that. For me, it's so natural. So I do not think about this, but let me see where's the best slide. Yeah, let's maybe take this slide here. So we have this electron motion which induces this current, and then over there's this resistor. So now you can imagine this electron oscillates back and forth, and that current is dissipated in the resistor, right? And so now you're like, oh yeah, that electron gets cooled because there's dissipation, and that energy has to come from where? And comes from the kinetic energy of the electrons. But then at the same time, the resistor is also causing Johnson noise, and that Johnson noise is going to heat the electron. So what experiments in penning traps with charged particles have shown is that in the end, that charged particle will be in thermal equilibrium with the resistor. And this is basically why it's meaningful to talk about the temperature of a single particle in the first place, right? It's a weird concept to begin with, maybe. And so why does this matter? And it matters because there might be anharmonicities in the trap potential, meaning that the trap frequency would not perfectly defined any longer, and then the phase of that oscillation is not a good measure any longer, because depending on how highly it's excited, it changes. So that's one concern. And it turns out that this also then has influence on the quantum gate. And then there's a much more fundamental problem we discovered only very recently is if you have two electrons. So we are so used when we look at the ions, we laser cool them and the ions crystallize in this nice Wigner crystal, and oh, everything is good. But when you look at it, electrons at 4 Kelvin, they would barely crystallize. So basically, the electrons do not switch places. But sometimes, it's a Boltzmann distribution, if they have more energy, they start switching places. And I can't do quantum computation if the electrons just hop around. So that's why we probably have to get colder. So 4 Kelvin is a little bit borderline. So this is where we want to really want to be at the 100 millikelvin. That's the main reason, I would say.
Okay. Can I ask you a very quick question regarding this point? Mm-hmm. So, I mean, if you get colder, I come from a very different angle and say that, okay, at the end of the day, you would like to have multiple electrons which are now going to interact through long-range Coulomb interaction. Yeah. So would you then get into problems like Wigner crystallization and other kind of, many body phases? Is there a possibility of that sort?
Yeah. So we understand that gate mechanism between the electrons. So you are right. If the electrons are too hot, this gate mechanism starts failing at some point. And so this is basically this calculation here. Actually, no, it's too small. It's too small. So this has something to do with the nonlinearity in the end of the interaction. one needs to be careful. But the gate as designed is to first order independent on temperature. But yeah, so this has something to do with the how this gate is designed. But to second order, of course, I get sensitive to this. Pretty sure that we looked at it. Yeah, I can check back with Jan what she found. We found that the dominant source, so she did the full master equation, that is really an emotional heating. And why do we? I'm pretty sure that we have the temperature also. We looked at it. Yeah, it was insignificant. Yeah, but you're absolutely right. If it's too hot, there's a problem.
Thanks.
And this has something to do with how the electrons move and basically whether the average distance of the electrons changes. Because if they are hot, the average distance of the electrons will change because the Coulomb interaction is anharmonic. This is then the fundamental reason why there are problems appearing.
Mm-hmm.
Right, and then the acquired phase shift becomes indeterministic, and that's the end of it, right? If the phase shift is not exactly pi/2 always, then yeah, we have a problem.
I think there are no other questions from the audience at this time. So let me thank Hartmut again for a wonderful talk. This is we are at the beginning of a very interesting phase, I suppose, with this system. So thank you for telling that. Let's thank the speaker once again, and subsequently we can close the session. Thank you.
Great. Thank you very much. And if you have any questions, please feel free to reach out and follow up.
Thank you.
Okay.
Thank you.
Bye-bye. Have a great day. Nice seeing you again.